Hi everyone, in this video we will be going to learn about basics of Boolean Algebra, including laws like commutative, associative and laws like that. So everything explained clearly with examples. So we have a separate concept called De Morgan's law. So it is also part of Boolean Algebra, includes zeros and ones. But this law is not included in this video. It is a very important concept. So we are going to cover this concept in a separate video with more examples. So let's get started with this video about Boolean Algebra, the basics. These are the laws that we are going to cover in this video except the De Morgan's law. So De Morgan's law is a very important concept, so we will be seen in upcoming video. So in this video we will be going to start with the AND law, OR law. So these are the very simple laws, so that's why we are going to start with these laws. So this is the simple overview of all the things that we are going to discuss in upcoming video. So these are the all categories. So all categories mixed here. So we are going to segregate these things, and we are going to distribute all these things to the separate laws. We have it's already, that is AND law, OR law, commutative law, like that. So we are going to segregate and separate each of them. So let's start. So before starting to learn about Boolean algebra functions or the simple formulas, so we need to know about what is the use of Boolean algebra, or where we have to use the Boolean algebra. So we are going to use the Boolean algebra in the minimization of Boolean expressions. So for an example, so take this as an example. So if you observe the y is equals to a plus b dot c plus a, so this is known as Boolean expression. So we are going to minimize this expression. So how we can going to minimize? So why minimization needed? So if not minimized, so it can take more gates. If after minimized, it can take only less gates. So if you observe there, it requires 2 OR gates and 2 AND gates. So it's take more complexity. So let's see the simplified Boolean minimization expression. So after simplification, it becomes like that. So if you want to know about how this minimization happens, so if you observe carefully here, only one OR gate is required and one AND gate is required. So it's very simple to represent like that. So we can able to minimize like that. So this is known as Boolean minimization. So we have to take common in a. So we have two a's in two terms. We have to take a common. So 1 plus c, that is again we have to 1 plus c is again that is 1 only. So how that is 1? So we are going to see that. So I hope you understood the usage of the Boolean algebra. So let's start AND law. So in the AND law also we have four things that you are seeing there. So these are the 4 AND gate requirements. So that I have represented there. These are the things can be used are all in the category of AND law. So let's start with the first one, that is a into 1 is equals to a. So basically if you observe or if you know about basic the logic gates, you can able to identify it is a AND gate. So AND gate means the product term, that is a into b is equals to y is equals to a dot b, we are going to get as output. So I also represented the truth table of the AND gate. So all are zeros except the last term. If both are ones, then only it becomes 1. So in the term that we are seeing there, that is a into 1 is equals to a. So if you observe, if you replace b with the 1, so you are going to replace output also with the y is equals to a into 1. So you are going to get the final output as y is equals to a only. So if you observe there also, if you have replaced b with the 1, we have b with the 1 as 2 cases, that is second case and fourth case. So if you see there, so the output is just depending on only a. If a is 0, output is 0. If a is 1, the output is 1. So simply like a normal math only, that is if anything into 1, that is the same thing that we are going to get as output. So as you've seen there, this is the second case in the AND law, that is a into 0 is equals to 0. So it's like normal maths only. So if anything into 0, that becomes the output as 0. If you observe there, I replaced b with the 0. So in the table also, if you consider the b as 0 terms, that is first term and the third term, the output corresponding to the b is equals to 0 is 0, the first term and the third term. So definitely whatever may be the 0, if the single term present 0 in that, so it is a basically AND gate, we have to multiply so that the output becomes 0. So this is the third case that we are going to see in the AND law, that is a into a is equals to a only. So in the normal math, it is a separate different thing, that is a square. So forget about that. So this is Boolean algebra. We are suppose if you take 0 into 0, again we are going to get 0. If you are going to get that is 0 only. So if you are multiplying with 1 into 1, that we are going to get as again 1 only. So Boolean algebra involves only 2, that is 0 and 1. So if you observe the truth table as well, the both are the same thing. So if you observe, that is 0 into 0, that is first case and fourth case. So 1 into 1 also 1. So that depends on the a itself. Both a's are 1, that is 1 only, that is depends on a, becomes a the final output. This is the last one in the AND law, or we also call this as complement law, that is a into a bar is equals to 0. So why? So if you observe the truth table, so we are going to discard the remaining things, because we are going to have just a and a bar. If a is 0, a bar is 1, just opposite of that. If a is 1, the a bar is 0. If you multiply both of them, we are going to get definitely 0, because one term is definitely involving with 0. The final output is a into a bar is equals to 0. Yeah, we successfully completed the first law, that is AND law. So now we are going to start with the OR law. So basically the name itself you can able to understand, that is AND means so the dot product is there in between, so OR means the plus sign is there in between. These operations are same. If you observe the four operations that we have seen above, so that and this is simple difference, that is plus operation is involved here. So let's start with the first one, that is a plus 1 is equals to 1. So the equation suggests that is a plus 1. So we are going to replace b with the 1. So I have put a table to, that is truth table of the OR gate itself. So if you observe, all are 1s except the first term. If both are 0s, then only it becomes 0. Otherwise it's only 1. So if you observe, if you replace b with the 1, so that is the, so b involving cases are 2, that is second case and the fourth case. If b is equals to 1, so the definitely output would be 1. So it doesn't depend on a, because so we have learned that only in logic gates. Logic gate says what? If anything with the sum 1, so that becomes the output 1. If one term also involves 1, that if sum them, then it output becomes 1. So that says the or output of the OR gate. The next thing that we are going to see in the OR law, that is identity law. So just like normal math only, so if anything plus 0 gives the same thing, that is a plus 0 is equals to a only. So that depends on a. If you observe, if you replace b with a 0, you are going to have two cases, that is first and third cases. So if b's are zeros, then it is depending on a only. If you observe, if a is 0, then the output is 0. If a is 1, the output is 1. I hope you understood there. You can also observe from the symbol also in there. So the next case we have in the OR law, that is a plus a is equals to a. If you add both zeros, that we are going to get 0. If you add both 1s, we are going to get, that is 1. So I hope you understood anything plus anything, the same thing, that we are going to get the same thing, because this is only involves binary, that is 0 or 1. So we have only two cases, that is 1 1 or 0 0. So 1 1 means 1, that is 1 plus 1, that is 1. Zeros, that is 0 plus 0, that is 0. So again it becomes only the same thing. So that is output itself is a only. You can observe in the symbol as well. So the last and final one in the OR law, or in the complement law, so that is a plus a bar is equals to 1. So if you observe, if you take, that is a, the a complement is 1. If you take a1, that is a complement is 0. So if you add both of them, take the first case, a is 0, a bar is 1. If you add both of them, the output is 1. So any of the one involves the one as that input, so the output is going to be 1. Definitely we know that in the OR gate itself, the property. So this applies there. So a plus a bar gives rise to 1. So I hope you understood there. The next law that we are going to discuss is commutative law. So basically commutative law means a into b is equals to b into a. So vice versa, to multiply or add in the reverse order, we are going to get the same output. So that is known as commutativeness or commutative law. So the dot product is same and the addition also same, that is a plus b is equals to b plus a. So if you observe clearly, I have put in the diagrams as well. So in the first diagram, we are passing in the symbol, observe in the AND gate symbol, that is a into b. So we are getting output a into b. So we are passing a b. So we are also passing b a. So it doesn't make any sense. So both are same. So in the OR gate also we are passing a b. In the second case we are passing b a. So both addition means that's the same thing, that is known as commutative law. The next law that we are going to see in Boolean algebra is associative law. So associative law means, so with what the separate thing is associated with. So if you observe with the dot products, so you can able to see a into b, so in brackets, so it is associated with c. So if you observe is equals to a dot b into c. So this both are same as you observe there. So if you observe with the sum also, a plus b is associated with plus c. So a plus b plus c. So both are same. I hope you can able to see there. It's a simple thing that we can able to understand. Both are equal. So we are going to analyze the associative law with the help of the circuit diagrams as well. So for the dot product, you are going to see that is a b dot c, a dot b dot c. So I am going to represent the first one, that is a dot b dot c. That is first we have to pass a b. So a into b I am taking as a variable, separate variable, that is p, a new variable. So again I am passing in that a c, a variable. So I am going to get final output as a dot b whole dot c. So the second thing, that is b c. So I am taking a new variable q, that is q is equals to bc, b dot c. I am passing a variable a, so I am taking dot product of q into a. So that is I am going to get y is equals to a dot b dot c. So this is related with the associative law. The same like with the associative law, that addition also. So we are going to see the separate thing with the help of truth table or ASO. So with the help of truth table we can able to understand very clearly. So if you clearly observe the truth table, so of associative law of the AND gate, so that is a dot b dot c is equals to a dot b dot c. So I hope you understood the circuit diagram explanation in the previous slide itself. So if you observe there, the p is equals to a dot b, that is a new variable that I have taken. So in the second one, that is q is equals to b dot c. So in the first one, output is equals to p dot c. In the second one, the output y is equals to a dot q. So if you observe, basically I have made a table that is a b c. So I have also included p q and y also. So y is the output, p q is the middle term or the outputs of the individuals, that is a dot b or b dot c, so that you can able to write with the help of the normal truth table of the AND gate. So you can, if you don't know about the AND gate logic, so you can able to refer the video that I am giving in the description box about the logic gate. So basically filling all the truth table, so finally we are going to look the table like this. So if you observe, so basically we are going to prove both the product terms are equal. So if you see the final output, all are equal. The final output is all are equal. So and the both of the y's are equal in the last case itself. So that is all are ones, so it is 1. So we are going to declare that both the terms or both the outputs that are equal, or inputs may be different but the output is same. So that we have to consider into consideration. So that is known as associative law. So in the same way, we are going to verify the associative law with the help of OR gate. So if you observe clearly there, so I am taking the same thing, that is I am taking new variables, that is p and q. So I am filling the truth table with the help of p and q itself. So if you observe, the truth table of output y is same for the p and q as well. So as the outputs are same, all are the first, except the first term, all outputs are same, that is 1 only for the both the first condition and the second condition as well, for the p condition and the q condition as well. So the outputs are same, so we are going to consider the output is same. So that is known as the associative law. We are going to consider the output itself. Since the output are same, so this associative law works. So both the circuits are same if you interchange also the variables. So as we are discussing the associative law, so up to now we have solved with the help of AND gate, OR gate. So but we also know that the associative law will also be followed for XOR gate and XNOR gate as well. If you observe there, if you XOR A, B separately with the XORing C, so that becomes the output, and if you reverse that, so if you took B and C the first terms and the A as second term, so the output would be same. If you interchange also the things, but the output would be same. So in the XNOR case also, if you reverse the inputs, so outputs also if you reverse them, both the associativity is same, so outputs would be the same, so the associativity would be the same. So we have discussed AND gate, OR gate, XOR gate, XNOR gate. So the remaining 2 gates, that is universal gates, so that is NAND gate and NOR gate. So we are going to check the help of commutative law and associative law also. So let's start with the commutative law for the NAND gate. So if you see the NAND gate, so that is output is a dot b whole bar. So if you reverse also, it doesn't make any change, so outputs would be same, so it follows commutative law. So if you see the NOR gate, so that is a plus b whole bar. So if you reverse b plus a whole bar, so that makes also same output, so that is also follows the commutative law, that we can able to say both circuits are same. So as you observe now only, that is NAND gate and NOR gate. So for the commutative law, both are obeying the commutative law. So if you reverse also, the output would be the same. So if you observe the associative law in the NAND gate and NOR gate, so that doesn't follows the associative law, because so this is the complex outputs. So we don't know about De Morgan's law. So we have to apply De Morgan's law here, and we have to check whether both the outputs is same or not. So if you observe the inside also, so upper bar is same for both outputs. The inner bar is for the first NAND gate, we have a dot b whole bar. The second thing, we have b dot c whole bar. So both make some different. So in the NOR gate also, we have a plus b bar. The second thing, we have b plus c bar. Whole bar is same, so I am saying about inner bars. So basically it doesn't follow the associative law. Remember this. So we are going to discuss in detail in the upcoming video in the De Morgan's law. We are going to apply that De Morgan's law in the upcoming video. Let's discuss about these two laws combinedly, that is distributive law and absorption law. So if you took an example over there, so this is an example that I have mentioned in the above slide itself. So that is a dot b plus c, that is equals to, if you, that is distributive law we can able to say. So that is not, it's like normal math only, we have to distribute the b plus c to the a. So after multiplying individual terms, so inside, so we are going to get a dot c plus a dot b. So if you observe the circuit diagram for the first one, that is a dot b plus c, so the circuit diagram would be looking like that. So if you observe the circuit diagram for the second one, that is a dot b plus a dot c, the circuit diagram would be like that. I hope you know how to draw the circuit diagram. So we have a dot, so if you observe the second one, that is a dot b, so we are going to have an AND gate. So the second term is the a dot c, so we are going to have an AND gate. So in between we have plus operation, so for that we have to have an OR gate. So finally we are going to have the output, that is a dot b plus a dot c. So for the first term also we have an addition operation, that is b plus c. So for that we have OR gate. So we have an AND operation also for that with a. So for that we also have AND gate. So both the circuit outputs would be the same. So that is known as distributive law. If you also see the absorption law, so the name itself indicates absorption. So absorption means so a separate variable. So we can able to see, that is an example that took from the above picture only, we have saw already. So there, that is a plus ab, so is equals to a, we have to prove that. So if you see there a plus ab, so we can able to take a common. After taking a common, we have 1 plus b inside. So we already discussed anything plus 1 that gives 1. So in the OR law, so that makes inside circuit, that is 1 plus b is 1 only. So with this we can able to say the b is disappeared, or we can able to say b is absorbed by the a. So it is known as absorption law. Let's decode another Boolean expression, so that I have already given above. So this is a plus bc, so that can be distributed. So that has a plus b dot a plus c. So you might think, so this is not possible in a normal math, how this is possible here? So in between we have plus operation, so this is distributive law. So let's check it out. So for understanding this, let's take the RHS. So that is a plus b into a plus c. So we have to multiply it individually like normal math only. After multiplying, we can get 4 terms, that is a dot c, b dot a, b dot c. So if you observe, that is a dot a is equals to a. So as we saw in the up only in the OR law, so we can able to observe in the first, second, third term we have a common. So we can able to take a common. So in the first term itself we are left out with the 1. So 1 plus c plus b. So how many may be the terms present in with plus? So if 1 is present, the whole output would be 1 only, because it's an OR gate. So how many gates we can able to say? So it's if 1 plus is present, that's it, whole output would be 1. So if c and b can be zeros and ones, anything it can be, but the whole output would be 1. So a into 1 plus bc, so the whole output would be a plus bc. So that's the, hence it is proved. That's the required thing to be proved. We did not do nothing new here. So we applied simply Boolean expressions or Boolean functions here. So if you observe, we are applied Boolean expression in the second term on the third term. So we are able to do simple minimizations. Let's have a look from the above examples only. So that is in the a dot a plus b is equals to a. So if you want to observe this, so let's take the first term common. So common thing can be multiplied inside. So that is a into a plus a dot b. So again we know that a into a is equals to a. So a plus ab. So again we have a common. So take a common, a into 1 plus b. So we have already saw that anything plus 1 gives you 1. So a. So the final output is a. So this is the required thing to be proved. So above expression hence verified. So you can able to see the above expression. So that is a into a plus b is equals to a. So this is the reason that I have mentioned 2 theorems or 2 laws at a time, that is distribution law and absorption law, because we are applying the first one, that is distributive law. So we are distributing that a plus b in the first step. So again we are able to observe the second term, that is b. So that is why combinedly I am teaching that distributive and absorption law at a time. So the last and final thing of this lecture is that Boolean expression, Boolean algebra is, that is a bar, double bar we can able to simple say. So if you observe, we have 2 NOT gates. So in the first NOT gate we are getting a bar. So in the second NOT gate we are getting a double bar. So a double bar is also known as a. Why? So if you have, suppose if you have 0, started with a simple 0. So if you flipped first term, so that becomes 1. So again you flipped, so what it becomes? Again 0 only. So we can able to say a double bar, or we can able to simply cut out those 2 bars. So if you have also 4 bars, so you can able to cut simply the 4 bars at a time. So if you have 3 bars, so you can cut 2 bars, so you can left with only 1 bar. So that's the motto you can able to think of. So 2 bars can cut off, like the 0 is tupled 2 times, so it becomes again 0. So this is also a part of Boolean algebra. And the last and final foremost very important concepts that we are going to discuss in the further video, that is De Morgan's law. In the upcoming video we are going to discuss. So these 2 expressions are very utmost important. So in the solving of XOR gate, so we already saw the video about the XOR gate, so the NAND gate implementation as a universal gate and the NOR gate implementation as a universal gate. So about understanding those 2 concepts, so NOR gate and NAND gate as universal gates, so we need to know about compulsory about these 2 laws. So we're going to see in the upcoming video.